Let's start. So I started the screencast. I'm going to randomly give some sort of credit to everybody who's here. So luckily you're here today. Put your name and student ID number on this piece of paper. And I'll make a list of these and it'll somehow count in your favor. So good job coming today. So it'll just go around the room. Okay, so here's what we're going to do today. Questions as usual. I'll make a few remarks about the next homework assignment, etc. And then we'll talk mainly about graphics, how to draw 2D pictures, 3D pictures, etc. using Sage, Matplotlib, R, etc. Okay? So before we get going with more things, are there any questions? Okay, no general questions. All right. So let me show you the next homework assignment. It has 3 problems. And it's due at the usual time, this Friday at 6. And I've gotten better and better at collecting, so probably will get collected at 6 this Friday. I spent the morning writing a bunch of nice, clean Python code that does the collection and redistribution, rather than the kind of disorganized worksheet that I had before. So things are getting cleaned up a lot regarding the grading. So here's problem 1. It's a problem that involves vectors in 3-dimensional space. Basically, you'll make a class that represents a vector with rational coordinates in 3-dimensional space. I know how various methods like dot product, cross product, addition, multiplication by a scalar, and so on. Okay, so really you're just going to follow exactly the sort of thing that we did in class last week. Okay? And I show you some of the methods and what it will kind of look like to get you going. So that's problem 1. And there's some discussion just letting you know whether you should have doc strings or not, what sort of methods are expected. Okay? And I encourage you to put your solution in a file, vec3.sage, so that you can doc test the file by typing sage-t vec3.sage. This is exactly how I put the rational number class in a file called rational.sage and doc tested it. So you'll follow a very similar procedure. Okay? That's problem 1. Problem 2 is almost exactly the same, except you'll make a Python class whose instances are elements of the Gaussian rational numbers. So the numbers of the form a plus bi, where a and b are rational numbers. So if you take a number like 2/3 plus 5/7 I, where here I is square root of -1. This is a complex number, but where the coordinates are both rational numbers. If you add together 2 such things, you get another one. If you multiply 2, you get another one. And it's slightly non-trivial, but you probably learned it in 8th grade. If you divide one of these by another one, say, the result is again of that form. It doesn't look like it's of that form, but you can rationalize the denominator. That is, multiply the top and bottom by the conjugate, and you'll end up with something of that form. Okay? So every element of what I've denoted by k right there can be written in the form a plus bi. And so what you'll do is you'll implement addition, multiplication, etc., just like I did with the rational numbers, and you'll put it in a file gauss.sage. Okay? And then problem 3 is to, based on feedback and possibly consultation with me and Simon, decide on a project topic and then put 2 hours of work into your project and record what happened. This problem will take you 2 hours to complete. You could do, yes?
Oh, sorry. For problem number 2, it says you recommend putting code
Yes, I do.
in a file. Does that mean that we have to? I mean, I'm not
Yes.
to it, I'm just curious. Okay.
You have
So recommendation is like recommend.
Well, I recommend you do the problem.
Okay. Just curious.
Just like you don't have to do the problem. But
It's true.
Credit if
You
you
recommend.
Yeah, but I strongly recommend you do the problem. Yeah. I mean, it's very hard to doc test it and stuff. It's not in a file. So, and it's really easy to just click plus new, make a file. Okay, so put 2 hours of work into your project, and and record here what you did. And the grader is going to look at it and say, does it seem reasonable that they really spent 2 hours doing what they said here? Your 2 hours could be spent reading various background material, like you might read some Wikipedia pages, for all I know. You could say, I read this page, I thought that was interesting. This still seems like a good idea for a project. Or you could say you read some code in Sage, or you read about various tickets. Okay, so that's what the project is. You should get full credit on this, but you should spend 2 hours and honestly say, yes, I spent 2 hours and here's what I did. Okay? Any questions about that? Hopefully it's really clear what I mean by problem 3. And a reminder, the first draft of your project, and we'll define more what that means, is due on May 9th, which is coming up soon, a couple of weeks. Okay, any questions about this homework assignment? So again, it's due on Friday, etc. All right, so there it is. You should find this in the home directory of your project. If you don't, let me know. Also, let's see. So I've made homework 4 and assigned it. The pure grading of homework 3 is available for you to do. So you'll find that in the grading folder in your project. And also the grading you did of homework 2 has been redistributed to everybody, so other people can see the grading. And if you want to see how you were graded on homework 2, you can look now. Just to remind you, everything's in the sort of similar place to before, but I'll just, let's see, open dot. Okay, so these are your projects, and we'll go to this one. Homework 4, which you're supposed to do, which somebody just opened 2 minutes ago. There it is. You'll find it in the homework 4 directory. Your graded homework, you'll see that there's homework 1 and homework 2. Homework 1's from a long time ago. Homework 2 just appeared 5 hours ago. And inside of that folder, you'll find exactly 3 subfolders, I hope. Yes, and in there, there's each one of them is a copy of the homework that you submitted, but it's been graded. And if you look it over, and I looked randomly, and I noticed one student had like 20 out of 20, 19 out of 20, and then 13 out of 20. So if your grading looks like that, you might want to look closely and see what the heck's going on, and possibly contest it. Because there will be at least one person with such a strange thing, I noticed. And then the other thing is grading. Inside of the grading folder, there's now a new folder for you called Homework 3, which should have 3 subfolders, one for each of the students you're going to grade. There's the Homework 3 grading guidelines that Simon wrote, which explains how to grade each problem. And then there's this file, Who's Who, if you're curious who you're grading. So you don't have to look. But if you want to look and find out who you're grading, you can tell. Okay, so that's it. All right, now on to any questions about homework stuff? Okay. Okay, now on to 2D and 3D graphics in Sage. So the idea here is, how do you draw pictures to illustrate mathematical ideas or data or whatever? And I'm just going to show you some things that you can do in Sage in this worksheet, since it's often very useful to be able to do this sort of thing. Okay, so basically 2D graphics in Sage. So here's how it started. In Python, there's a library called Matplotlib, which you can use to create 2-dimensional graphics, like lines and circles and all that sort of thing. It was written by a guy doing neuroimaging of monkey brains, and he was a MATLAB user, and all of his colleagues were MATLAB users. This was like 10 or 15 years ago, I guess. And so he wrote a Python library that was very similar to MATLAB, and it was available, and just a free open source library. And there were other approaches, but his just became super popular compared to everyone else's. And it's the most popular library for plotting in Python in general. It's called Matplotlib. But people doing, I don't know, more pure math stuff rather than drawing pictures of monkey brains and related data don't find the sort of commands that MATLAB has for plotting to be so convenient. For example, if you want to plot sine of x or something like that, you end up having to make 2 lists. One is a list of values of x, and the other is the values of sine at those points, and then you feed those 2 lists into a function, which in the context of visualizing a lot of data that comes up numerically is extremely sensible and very natural thing to do. And it's really the best way to go. But for visualizing a lot of things that come up in math, like calculus problems you're doing or whatever, it's often kind of annoying. And so in Sage you have another thing. So there's a student, Alex Klimashaw, an undergrad. He wanted to do some development on Sage, and so he sat down and started working, and he's like, what should I do? I'm like, well, how about if you crack open the Mathematica documentation, which has a very different approach to plotting things, and come up with a Python-ish interface to plotting, which somewhat follows the general approach of Mathematica. And of course, behind the scenes, it'll really just use Matplotlib. But it'll feel like you're using Mathematica. And so make that plotting available for Sage. And so that's where this originally came from. And then many other people have, kind of like Jason Grout, Mike Hansen, me, and others have revamped the code over the years to clean it up. And the fact that it was supposed to be very similar to Mathematica got forgotten by various people, and so that kind of got lost. But it still has some similarities and differences, and some nice unique innovations. Okay, so I'll just show you how to do a few things, like plot the sine function, how to adjust the parameters of a plot, like make the line thicker or thinner, choose colors, that sort of thing. And then also how to combine different elements to make a plot that involves a whole bunch of different things. And then finally, remind me to show you how to animate through a sequence of plots, because that can be fun. Okay, so let's see. I'll just go through some of these things. I'll start with just plotting the sine function. So it's really short. This is a plot of sine of x. And there you are. It's very, very simple. When you make it, if you use the plot command and don't give anything else except some callable, it'll try to call it with floats between -1 and 1, and then draw the corresponding plot. That's the default range that it uses. The plotting is actually pretty clever, though, as I'll illustrate. So you can give a range of values. Like, let's say we want to plot from -1 to 10. And so that's a second argument you can give. It's a tuple or list with two things, and it's the range of values. And notice the x-axis varies from -1 to 10. Notice also here you have an x and a y-axis. In MATLAB, you typically have like a frame around the outside, whereas here you have, in more mathematical applications, it's kind of nice to have an x and y-axis. They're just different perspectives on what you're plotting. That said, if you want to have a frame, oops, that's something you can just add. Like this, frame equals true. If you say that, then it'll switch to just using a frame around the outside. And if you want to get rid of the axes, you can do that. There's a lot of options like this that let you just turn on and off various aspects. And then you think, oh, I want grid lines. So you can do that. And now you have grid lines. So you can turn on and off all kinds of things. Notice that these are really properties of how the plot is displayed, not of the plot of sine. And so that's a little bit subtle and will make sense in a minute. And I'm just going to show you how you can customize things a lot. Another thing you might want to do is, maybe you want your plot to have a different color. What's your favorite color? Somebody? Green. Okay, you want it to be green. So you can make it green, maybe dark green so it looks good on the display. There's a bunch of words that are built in. I remember adding some table. So there's a bunch of standard words to describe colors. You can also use standard RGB color codes like the hash and then RGB like you would use in HTML. You can also say RGB as a function and then give it as input 3 numbers between I think 0 and 1. And you can also use HSV for different color spaces. There's a lot of different ways to describe colors. And if you can't remember colors at all, you can make an interact like I showed you before. And just make up any color you want, and I think I have to do show here. Of course, you can easily Google and find colors online, but this is another way. So now I have a little selector, and I can select different colors, and it'll, like if I want just the right shade of green, then you can do this and select a different color of green. Okay, so I'll just leave that code there. But the point is there's a lot of customization you can do. There's other things, so that's green, but maybe we want it to be thicker, so thickness equals 5. So now it'll be all nice and thick, etc. So if you want to draw a plot, it's pretty easy. And if you do plot question mark or then you'll see a list of these options, and there's a very long list. You can make it so the line is dashed or dotted or whatever. And the properties of the line, they're actually the same codes that you use in MATLAB. So there you are. So that allows you to draw a plot of a function. Be a handy thing to do. Let's see, there's a lot that, maybe I can't remember a lot of options for plotting. So let's see. Oh, there's some things for like log scale, log scale, semi-log y, etc. See some stuff dealing with polls. You can add a legend. Let's see. Hue, RGB color. Alpha. Oh, alpha is kind of fun. You can make the line somewhat transparent. And most of these options work for all the different plotting things we're going to consider. So you can use alpha equals, say alpha equals 0.5, and then the thing that you plot will be transparent, or 0.7. Anything, the alpha value determines the amount of transparency. So if you combine multiple plot elements in one, that can help you to control what one looks like when it's on top of another. So it's kind of fun looking. Oh yeah, and just some examples of dotted, dashed, etc. Markers. I don't know. Whenever somebody thinks, oh, I want to add something to Sage, this is always a tempting target. So it's got really big. Fill color. Oh, this one's fun. Fill color. So if you say, okay, maybe that means nothing here. Maybe I have to say fill equals true. What this does is it fills things in between the x-axis and your plot. This is nice if you're doing integration and you just want to see the integral. So as you might imagine, this is pretty powerful. And the thing I put here is sign. It can be anything at all that you can call with a floating point number, and the result can be turned into a floating point number. So you can write a general Python function. You can use any sort of symbolic expression you make, like, I don't know, sine of x cubed over x, whatever. And there's some really clever stuff going on behind the scenes. For example, if the thing that you're plotting is a symbolic expression, so something like sine of x times cosine of 2y, or actually one variable, it will compile the expression into an internal form that's designed for extremely fast evaluation. And so in order to draw the plot, of course, it's evaluating the function at a large number of points, but it can do that ridiculously quickly using some fast compiled internal form that it uses. So there's that. It won't be as fast if you just make your own Python function because it doesn't compile it to some internal form. You can also make the thickness really small too, which can be fun for a plot like this. So now I made it 0.1, and notice it's really, really thin. One thing that you might be annoyed by is, this is a high resolution display, so it's not so annoying, but this is a PNG image that it's drawing in the output. That's good because you could just right click on it, save image as, or say open image in new tab, and you'll see it's just a PNG image, which is easy to put anywhere, but it's not good really for including in some sort of document because it's a bitmapped image. There's just a lot of dots there. It's not a vector graphic where it says, where you give like lines. However, it's easy to construct the corresponding vector graphic if you want. You have to assign this to a variable. Oops, sorry, I did bottom of page. But if we assign it to a variable, I'll just call it maybe G for graphics. You can still display it by just showing G, but you can also do g.save, and then there's a whole bunch of different file types that you can save as. You can save it as an SVG file in case you wanted to use it in Inkscape or Adobe Illustrator or something. You could save it as a PDF file, a.pdf, which is really good for inclusion in a lot of different documents, like in LaTeX documents and so on. When you do save, it just creates a file in the current directory with that name. So if we now look in the current directory by clicking on Files, and of course all this works the same anywhere you're using Sage, there's a file a.pdf. If you click on that, you'll see that it's a PDF, so it's now a vector graphic. So if you zoom in really, really close, you will still have quite a lot of detail. which if you're a professional illustrator, you'll appreciate a lot. So these are not just pixels. It's like the information of how you're supposed to render to, rather than some pixels at a certain point. So that's important. And that's the sort of thing that Matplotlib provides. And it's the sort of thing that, in 2008, it was really flaky, but nowadays it's really good. So it used to be, oh, we can render in PNG, that works, and then PDF, oh, there's somebody working on it, it's sort of halfway hackish, and some things render fine and other things are completely broken. But now it's really, really solid. And there's other formats as well, like SVG. If you do, I think, show G SVG equals true, it'll display this plot in the browser using, in this case, Google Chrome's SVG renderer. That should probably be the default for displaying plots, except that Google Chrome was extremely buggy regarding SVG rendering until about 6 months ago, even though other browsers were really good. It's actually amazing. SVG rendering, I don't know if you can tell the difference, but on the top, if you look closely at these numbers, they're really pixelated compared to these. You probably can't see it you can't see it up here, but I can see it on my Retina display here. Maybe if I zoom in, you can see the difference. I don't know, maybe not, but trust me, the bottom one is crystal clear and the top one isn't. So I'll probably just switch that to be the default. In any case, you can make professional quality illustrations that you can include in other documents meant for publication in a journal or something like that. Oh, and okay, one other thing to mention about plot is it has an adaptive refinement algorithm. So what it does is it chooses some number of points, which is one of the parameters you can specify. I don't know what the default is these days, in the interval, and it randomizes them a little, jiggles them a little, so that they're not like all equally spaced. It's easy to make up examples of functions where if you plot the values only at exactly 100 equally spaced points, it might look like the zero function, even though it's actually some really random looking, crazy looking function. Like you can do that with sine of 2 pi x over n, where n is the number of points that you're going to plot at. So that would be very misleading. So what it does is it jiggles the points just a little bit, then it evaluates the function of all of those points, and then it starts drawing the plot, but then it looks and sees if there's like a big difference between two successive points, and if so, it'll fill in additional points there recursively. So even if your function is sort of really crazy at some points and really smooth at other points, it'll look like it should at every point. So it's very good at dealing with that sort of thing. This is exactly the sort of stuff that MATLAB isn't at all good for plotting, but Mathematica is, and Sage is also. And the reason it has all that adaptive refinement was that at Sage Days 9 in Simon Fraser University, a bunch of students just decided that was the project they wanted to work on, and they spent the week implementing adaptive refinement and making plotting much better. And so there's like recursive cutoff limits and stuff. Okay, so that's the plot command. So it's pretty powerful and lets you make nice looking plots. Okay, so let's see, what else? So plotting a function. Okay, I'll show you a few other things. But there's one crucial thing. Watch this. So if I do plot of sine from sine of x, I mean, the x is optional. You can be more explicit and do things like this. Say from 0 to 4 times pi. So you can make a plot like that. Let's make it green. And then we can make another plot, maybe of cosine. And I'll make it dark blue. So these plot objects are just objects, they're just Python, they're instances of a Python class, just like anything else. And you can assign them to variables. And when you, basically their repr method, which gets called when you just give the thing by itself like that, is to just show the thing. But the repr method does something to display the image here. It calls a function that which is, say it calls this function solve as file, and it gives some identifier for some file that it creates. So that, but here's another thing. Let's suppose you want to combine the two plots. What you do is you just add G and H together, and that combines the two plots. So now you can really make complicated scenes. If you have plots of a couple of different functions, and then some circles, and whatever else, some rectangles, some text, all kinds of different things, some lines, etc. You can add them all together using plus, and you'll get the scene that's what you get by superimposing all of those graphics objects. Yes?
Is it possible to make the x-axis in increments of pi?
Maybe. I don't know. That's a good question. So let's see, g.show. I think show is where we'll find all the documentation about controlling axes. Wait, this is, oh crud. Maybe save. Hold on, let me look for a second. I think that the axes marks are customizable, but I'm not sure. Legend labels. And the answer is probably yes, because the axes are just generated via Matplotlib, and it can do pretty much anything. So probably yes, but I don't know how to do it. Maybe g.axes. I see something called axes labels, but I don't think that's what you want. It might be tick.
Sorry, what's the question?
It's can you change the tick labels, basically?
Yeah, you
completely customize it. Oh, isn't there? Oh, you've used that. You can do you can pass functions in, right, that allow you to customize.
I can't remember what the exact
Yeah.
is. If you dig deep enough, there is a command which allows
Yeah.
you to manipulate all of the data labels from each of the axes.
And I think you can pass in custom functions, so you can really, really customize things. But I've never done that. Usually, yeah. It's pretty ridiculously customizable. Okay, so let me just show you a few other things. So if you have a sequence of points and you want the line that goes through them, so well, of course there's no line that goes through these. It's just weird. But if you give a sequence of points, it draws a sequence of line segments that connects them. So we're not in some weird universe where that's a line, but this is kind of a result of copying Mathematica. In Mathematica, there's a line function that has these semantics. But this is, in fact, an extremely useful command, especially because you have complete control over exactly what's getting plotted. It doesn't do any adaptive refinement behind the scenes. It's especially useful if you're trying to plot something and each data point takes a lot of time to compute, and you just want to plot exactly those points. One thing that I've often used, which probably should be an option to this, but you make like a list of points. These can be two tuples, whatever. You can do line of v plus points of v. And that'll superimpose the two plots, and so you end up with your sequence of line segments, and you have little dots on the vertices. And I think it looks cool. Maybe make these gray. That looks pretty. Okay, and now, for fun, you can make this v programmatically in some way. Let's make a random walk in two-dimensional space. So what we'll do is start with the point 0, 0, and then for I in range, I don't know how many steps should we take? 20 steps, okay? All we have to do is we need to append a new point to v based on the current point that's there, on the last one that's there. I'll just call it last. So v minus 1 will give us the last point. And now we're going to make a new point, which will be, we're just going to add something random to the x and y coordinates. Okay, so how do we get something random? There's different ways, but there's a function random that's imported by default, which gives you a number between 0 and 1. So I'll just do random minus 0.5. So that'll give me a number between minus 0.5 and 0.5. Okay, so when I run this, it's going to going to start at 0, 0, and it's going to go randomly, each time stepping, a little bit from the point we were at, 20 steps, and then in the end, we're going to have this random walk. So let's see what it looks like. And then the code at the bottom is going to plot it. And there it is. So went all over the place. Okay, I want to make it bigger. Can't resist. And there you are. And of course, if you do it again, it should look completely different. And it does. Let's make it even bigger. And having no trouble handling this, of course. So, neat. Random stuff is kind of neat. And I think the dots are way too big. And another thing, like line, just like when we were drawing plots of sine and so on, you can change the thickness, the color, etc. So if I do thickness equals 0.4, it'll be a lot thinner. Maybe I can make the color purple, etc. Okay, so just a little bit of code. It's giving us some neat little random looking pictures. So again, I make a list with one point in it, and then 2,000 times I take the last point in the list, what d square brackets minus 1 does, and then I add so the function random gives me a random number between 0 and 1, and then I just add that, but I subtract off 0.5, so that's between minus 0.5 and 0.5, and I just keep doing this repeatedly, and I get a random walk. Yes?
There's one command or parameter that I use a lot also, which is aspect ratio.
Ah, yes, because this thing looks all funnily squashed.
Aspect ratio, then just do aspect underscore ratio equals 1.
Okay, so nice, that looks way better. And I think this one will look better with SVG is true. And there's also a fixed size option, so I could do fixed size equals 10, and it'll be a lot bigger. So there. Few lines of code. And what would you do if you wanted to make every line segment have a different random color? How might you do that? Any ideas? Yes?
Would you do RGB values and then use random?
Yep. And then would you have just one called a line, or would you have to have a bunch of them, or what? Given what you've seen so far. What could you do? Yep. Yeah. So you can iterate through pairs of consecutive points, construct a line object for each pair, and keep adding them to some big plot that you're making as you go. And for each one, you set the color differently. That would get the job done. Might be a little slower than something else, but it would get the job done. And since it's so fast anyways, probably fine. Cool. What if you wanted to change the point sizes as you went? Make them all random. What would you do? Yep, exactly the same thing. Instead of using points, you'd have to use a point command with 1 point each time, but each time you add in a new point, you change the size randomly in some way. Or you might make the point bigger and bigger as you go to somehow have a sense of which direction the random walk is going in. Cool. Okay, so that's our random walk. And of course, it would be really fun to do this, but with different distributions instead of the uniform distribution on -1/2 to 1/2, which I just used. Okay, so let's see, what else do we want to plot? There's a polygon command. It takes a sequence of points and draws the polygon that you get from them. If it's not convex, it can look funny, but here you are. Whoa, that's a sequence of 3-dimensional points. So that isn't what I meant to do, but here's a polygon in 3D. Cool. I really meant to show you a 2D polygon. Some of the plotting commands, if you give if you give it a point with 3 coordinates rather than 2, it will find a point in 3-dimensional space. And that's actually what will automatically get plotted, which could possibly be confusing. Okay, so there's a polygon in 2-dimensional space. determined by those points. If you wanted to make it yellow, what would you do? Yep, color equals yellow. It works. Just what you think. And there we have our yellow polygon. And if you wanted to figure out how to, put a dark line around the outside, what might you do? Just look at the help. There's probably some option. What? Yeah, something. I don't remember what it is off the top of my head, but there's got to be. Or maybe there isn't. What? Or maybe the documentation's under Polygon 2D. That's what it says to do right here. It says further information is under Polygon 2D. Yep, okay, so there's fill, thickness. So, the thickness of the border can be controlled. So, yep, of the polygon itself. So I think that's what we need to try. Hopefully it doesn't. It might be yellow though. What? Sorry, what equals false? Fill equals false. Okay, cool. Oh, so what if we wanted to still have a yellow inside? Okay, let's try that. That would definitely work. Okay, so I'll have the outside with a black border, and then B, do the same thing, but with fill equals, well, the default's fill equals true. Nothing appeared because I didn't plot it. And there you are. And don't need that thickness. Cool. In my mind, it should be black. So, because it looks, it's pretty ugly, but there it is. So, and there's things I think you can take. Let's see. I'm not sure how much this works like with 3D. With 3D, you can create a scene like this by adding together a bunch of objects, and you can apply all kinds of transformations to it, like translate, shearing, etc. I don't remember whether we did that with 2D graphics. Let me check. If we didn't, that would be a good project. But it would be nice to be able to do g.rotate, for example. Hey, it's not there. Huh. There's no g.transform. Project idea. Wouldn't it be natural to be able to take a scene with a whole bunch of things in it and then apply a linear, various affine transformations to that scene and have everything get rotated around or squished or whatever? We do have that in 3D, but apparently not in 2D. Unless you're about to say we do. What?
No.
Okay.
How do you get the explanation of the class to pop up in like a separate window?
Oh, I hit tab. Yeah.
That's really annoying.
When you hit tab, it pops up in a separate window. If you just hit return, it just displays it in the output. Yeah. The window isn't very pretty though. It was like one of the first things I implemented. I haven't got back to it. It doesn't syntax highlight the code, but it works.
It doesn't take up a ton of
Yeah,
safe worksheet.
that's true. You might want to have another worksheet open just for help if you're doing a bunch of things. So, yeah, so apparently there's no like transformations of a group of objects, which would be a pretty good thing to have. Let's see. There's a lot of other things. I barely showed you the plotting, so I showed you a couple of things. Let me show you animation. So there's a command animate. It's pretty. Basically, you just give it a sequence of plots, and it will create an animation that steps through that sequence of plots. So what do we want to animate? Yeah, that's a good idea. Let's animate our random walk. Oops. Okay. So now I'm going to go back to 20 because each frame takes a little time. And now I want to. Okay, my goal is to animate this random walk here, so you can see it happen. And the way I'm going to do that is I need to make a sequence of plots so that each successive plot gives me more of the random walk. Okay? So, I think we'll just start with, I'm going to change the code a bit. So I'll say P is 0, 0. And then, this last is, to be careful not to change. equals P equals, okay, so this will give me, okay, so my plan is the following. I'll make an empty graphic, G equals graphics. That's a completely empty plot. And then, at this point in my code where the cursor is, I have two variables defined, last and P. P being the point I'm at, and last being the point right before. All right? So what we're going to do is we're going to add to the plot G, the little line segment that goes from one to the next. And, oh crap, we have to make a different graphics object each time. So I don't know if we can, that could get annoying. I don't know if there's a way to copy it. If we keep adding to it, then it will keep changing and it won't work because we'll just have the same one, the one with everything in it at the end. So
Can you just make a list of graphics?
yes, that's what I want to do, but which I definitely will have to do. So V will be our list of graphics. It's just I'm concerned because I don't know if there's a way to take a graphics object and copy it. It's the same issue with like a list. It's mutable. And so let me see if there's a copy method on graphics. I don't know if G is a, it doesn't seem to be. That would be a useful thing to have, wouldn't it? If you could take a graphics object and just make a copy of it. Something like that would be what I want, but I don't think that exists. Yeah. Okay, well, I can't do it that way. So that's annoying. Okay, what I'll do is the following. So, okay. This will be our collection of plots. I'm going to start with the previous code because what I was writing assumed that you can make a copy of a graphics object, which you can't do. But that would be a great project for somebody to add. Make it so you could actually make a copy of a graphics object. Just like copy and deep copy work. Okay, so basically what we need to do is what you said, which is we'll have all of our plots in a list, and then for I in range 1, 20, do this, and that'll do it. So we're just going to completely separately, except, crap, these are random, so that doesn't work. All right, let me make the random walk first. Sorry that I have to keep doing this. Okay, so here's the strategy. I'll compute the random walk, so it's a sequence of points, at the top. The random walk is now computed. Second, for each I from 1 to 20, I'll take the first I steps of the random walk and draw that plot and add it to the end of my plot. Okay, so right here, I need to put square brackets I. What that does, square brackets colon I gives me the first I steps of the random walk. And now G will be that part of the plot. And now we'll record G in our list of all plots, plots.append G. And now we've got it. And it would be a good idea to include this aspect ratio thing, just so it'll get carried over. And another thing you learn quickly with these things is, well, I'll show you. You'll learn it as you see. Okay, so when I run this, I shouldn't output anything, but I should now have a list of length 20 consisting of a bunch of plots. Okay? If I were to print out that list, I'd actually see a whole bunch of plots, I think. So if you do plot 0, you see the very beginning. And if you do plots, say 18, you see the end. So what we want is an animation that goes from the start to the end. All right? And now that's the easy part, except there's going to be a big annoying problem, which I'll show you how to deal with. Animate plots. If you just do that, it will go off, and it takes a little while. It renders every single one of the plots as an image, and then it runs some standard Unix tool to combine them all into a single animated GIF. This is a really ugly way of doing this. You can do it much better using other techniques, but at the end of the day, you do get a nice animated GIF, which you can stick anywhere you want really easily. It doesn't require any special player or anything. But it's a little annoying because it takes a little while to do each frame of the animation, as you see it's taking a while to do each frame of the animation.
Are they the same scale?
That's the problem. Yes, they're not. The X and Y ranges are going to be different from one to the next, and so it's going to look terrible. It's going to be jumping around as it goes from one to the next. Or maybe it won't look terrible. I don't know. I've never done this particular thing before. Pretty annoyed how long this is taking, though. Jeez. Come on. I'm surprised it's taking this long, so it's only drawing 19 different images. Surprising. That looks dubious. I don't know, something. Something may have gone wrong. Because I don't see like a lot of work happening in top. I'm just going to restart it. Because, I mean, it should take a little time, but not that much. I'll just make a really short one. Okay, so it's very, like, it has, wait, what? Oh, right, I still have. Okay, it has 4 steps, and now animate. Okay, so it is flipping through those 4 steps, but it's very annoying because the X and Y axes ranges are all over the place. And so you really want to control that. And you can do so by, well, one way is you can set, like, when you make the plots, you can set a max and a min. Whoa, your system has run out of memory. Really? Well, that's not good. I don't know which thing ran out of memory, but okay, it's strongly suggesting Google Chrome used up all memory. That would be a memory leak. Huh. Kernel task, whatever that is. Okay, I guess quitting Google Chrome. Technical difficulties. Pictures of children. Sorry. Okay, so, all right, so having technical difficulties, I'll summarize. We'll talk more about 3D stuff next time. We'll also talk about how to use Matplotlib and improving animation. It's kind of dumb making an animated GIF. It should automatically fix the scaling stuff, but it doesn't. That would be nice for somebody to do. And we'll also do a little bit with plotting with R and so on. Okay, so I'll see you on Wednesday. Soon.
When I reopened my Sage worksheet,
Yes.
things got all kind of jumbled around on it.
Okay, did you restore from the latest snapshot? Or
Well, I just fixed the code,
okay,
and then
jump
took
around,
some
that sucks.
screenshots of it right before 6 o'clock.
okay,
So I have a record of what.
okay. I didn't do any
wanted
collection
it
until
to be.
Sunday.
Okay.
So as long as it was fixed by Sunday,
Well,
and it
then
should be
when I
fine.
opened it back up on Sunday after you sent out the email,
Yeah, it was.
some of the where I had done the doc strings, the quotes had come off of them.
Whoa, which browser are you using?
I'm using Google Chrome.
On what operating system?
It's Mac. I think I'm on Maverick.